Hi friends. So today I will tell about I will continue the spectroscopy course progress. So usually, as we can recall, there are four models we generally four quantum models we generally read in perspective of spectroscopy or atomic spectroscopy, molecular spectroscopy, electronic spectroscopy. Among them, these are the very four important. There are so many models. I repeat, there are so many models, but among them, four are very important. Even which field you study, understanding these four and having a knowledge of these four is very crucial for any research field. So I will start about this as well as I will start about concept of multi dimensions in these models. Usually we are only studying the one quantum number, which is here n, j, n. This is for one dimension, but if there are multiple dimensions, then these quantum numbers will increase. How it will be, I will explain this. So please watch carefully and listen it. So these are the four models: particle in a box, rigid rotor, quantum harmonic oscillator, and hydrogen atom. And those energy formulas are here. These energy formulas are actually derived from the solving the Schrodinger equation of their particular models. So these four equations are really important even if we are physics chemistry. In chemistry, quantum chemistry, these equations are very important, as well as in physics, atomic and molecular physics, people need to know these equations. So I already made a video on this. You can look into that first. So we will continue now. So we will start with a we'll now see how we can insert many dimensions in this model. So firstly, if we start a simple model with particle in a box, this is the formula: En equals to n square h square by 8ml square. So here n is the quantum number for this model, and the L is the length of the box. Let's say we will first start in a particle in a one dimension box, meaning there is only, I'll take cursor, meaning there is only one dimension perspective. The particle is only confined to one dimension. Let's say to this segment, which has around axis length L. People even will write, so now the x dimension is finite. So any other, so in this region, it's only confined to this region, and people sometimes write another axis also, which saying the here actually this mean infinite means potential is actually infinite. After this, only in this region potential is zero. Actually, it's little complex to tell insert potential terms and explaining, but you can understand that that particle is only confined to this box. It cannot come out from this length of the another box. Why it won't come? It because of the influence of the Hamiltonian imposed on this particle. What does that mean is, let's say atom, let's say hydrogen atom. One electron is inside that atom. It's very hard to remove that electron because the nucleus is keep on attracting that. It's very hard to remove that electron, but with chemical reactions we can remove that energy. If we won't provide, that is confined to that atom only. So likewise, it's like mimicking this model into that, meaning it is until unless we supply energy, the electron will always only reside in this finite dimension only. And mm, in since it's only one dimension, let's say that quantum number is actually this one: En is equal to n square h square by 8ml square, and the n is the quantum number. And if we now go to another dimension, and if we confine the particle in a two dimension, let's say in x axis L and y axis in L, now it's a square. And anything other areas, the potential terms, let's keep infinite, so it's only confined to this region. So in that case, it will be, energy formula will be this: one term for the x dimension and another term is for the y direction energy formula. So here two quantum numbers are came, like nx and ny. Previously it's only one dimension, so one quantum number. Now we have two quantum numbers: one is in x dimension and another is y dimension. And yeah, those two are the quantum numbers. And yeah, and if we like to simplify this equation, if we isolate these into like this, and this is the simplified version. So here like and if we even more simplify, the final equation will be this. And if we cancel those and this is the final equation, sorry, this is the final equation. And same as like a particle in a 3D box, like if we confine the particle in 3-dimension box, then this is the energy formula. It will repeat 3 times for each dimension, length constraint, and each quantum number for that. So this is the energy formula, final energy formula for the 3-dimensional particle in a box model. This is for 2 dimension and this is for the 1 dimension. And these energy formulas are really important, and I will explain now the concept of here only. As we increase more, the degeneracy concept will come. What does that mean? I will explain in the next slide. So let's say we have this formula for particle in a box, and this is for 2 dimension and this is for 3 dimension. Let's say we have and if we draw energy formulas, so E1 has h square by 8 ml square, and E2 has this much energy value, and the E3 has this is the energy value, and E4 has this is the energy value. This is the gap between two energy levels, that is 3 times of this unit, and as it's like that. So if we fill electrons, it's like that. But in a particle in a 2 dimension, we have two quantum numbers. So let's say the ground state is actually E11. Let's say we substitute E11, then that is the energy formula for this. So it will have 2 times of this number, just it's a add-on quantum number value. And if you take the next one, E12, let's say E12, it will have one energy formula, and E3. And if you see, so here you can see, so in E2 there are two energy states. If we find the energy formula for these two states, it's equal. Like I will explain. So if you see, so these two energy states will have same value. Actually, if you substitute 2 1 in this equation, you will get 5, and if you substitute 1 2 also, it will come 5. So we found at a same energy value, we have two states. These are actually degenerate states, means like with the same energy value we have two energy states, and we cannot distinguish these two. Let's say only 2 electrons will occupy each state, then here it can occupy 4. It can occupy 4 electrons in this energy state. So that is what we have, two degenerate states here. And if you see, so next energy level, which is actually E22, there is no degeneracy, means if you flip, it is again 2 2 only. So this is the one state. And again, if you see the next highest energy state, this is 3 1 and 1 3. And likewise we have two states, degenerate states for each energy value, except same terms. And if we find for a 3 dimension, then it will be like, let's say the ground state is actually E11, and if you change to, you can find 3 energy states with the same energy value. And like the degeneracy here is actually 3. So this state, second state, has 3 degenerate states. Likewise, there are so many cases you can find which has degenerate states. And and these are the degenerate states in the particle in a box model. So each model has its own degenerate states for each level, energy level. One of the very much popular degenerate states is actually spin degenerate state, which is actually arises in the hydrogen atom model. So this is in a particle in a box model. These are also degenerate states, but these are not that much highlighted in degeneracy concept. But this is a one example of to you people to understand what is actually degenerate. So I hope you understood what is a degeneracy means. The degeneracy means the same energy value at two different states. We found two states with the same energy value. So that is what the degenerate states means. So we will explain about we will start about this hydrogen atom model. Here actually you will find 4 quantum numbers, and previously we have like each dimension we are classifying it as a x dimension quantum number, y dimension quantum number, z. But here actually we have special kind of namings for each quantum number. That is a principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number. Actually these three will only be there. This will be actually degenerate to these states. So and this will arises in different aspect, but actually these three states will be are actually more there. So these three are came for the 3 dimensions, like 3 dimension spherical coordinates. Hydrogen atom will be in spherical coordinates. Previously particle in a box are in actually in the Cartesian coordinates, but in a spherical coordinates we named each dimension with a different meaning: principal quantum number, azimuthal quantum number, magnetic quantum number, meaning each quantum number represents one dimension of them. And that is the address. Like if I say E11 in 3 dimension, here I wrote as commas, but people can even write like a bracket E1, E2, like that. So you have to understand each person's style of writing. So I written here like this, but people even write 2. So you have to understand that's the energy state and actually representing that value. So likewise here we have 3 quantum numbers more important to address, to locate where one energy level is there. So we have special nomenclatures also. You might have remembered that one is S is actually the azimuthal quantum number, one is the principal quantum number. So that I will explain detailedly in another video, but to understand about this, and actually in these things now these are degenerate, right? But we can make them split, meaning we can split them into different energy levels. This we can keep lowest energy level, this we can mobilize this energy level to here, and this we can keep here, and we can rank like we can make these energy levels modifying. We can split, that is called splitting, or also known as regenerate regenerate or splitting. These states we can split with the help of some perturbations. If we disturb, if we apply the, if we disturb the potential Hamiltonian term by including by giving some perturbation meaning by some potential. Let's say if you kept a electric field near to the this model, then it will have different energy configurations. Why that is, actually it will be root backs to again to Hamiltonian. I will explain it again, but first remember, just you need to remember that these states, instead of degenerate, we can split them. Then the electrons will only have energy at that particular point, only one state, and again if it want to accommodate, it have to go to the another ranked energy state only. So in a hydrogen atom, this is actually due to the, these are actually in second orbital we have actually 4 degenerate states. In E1 we have only one. These all combined we can write as 2, and this is called the principal quantum 1 2. If you see, if you study hydrogen atom, they will explain about the Lineman series, Balmer series, like that. If let's say this is the highest electron occupied level, if it is here or anywhere, when it relaxed, it will emit only the same kind of energy. So we cannot so like there is we cannot identify which state it is coming from. That is what another degeneracy feature it has. And we can keep we can identify them all like in only one energy state. Likewise in third also we have these main energy states. These will get splitted if we apply if there are multi-electron system. If there are multi-electron system, due to the perturbations of other electrons, in a single electron this will be the energy structure, and this will be the degenerate states like for that hydrogen atom. But in a multi-electron system, these are actually the electronic configuration looks like oneness, and this will split into like this, and this will split into like this, and it will be splitted due to the perturbations of other electrons in the atom. So atom is also a quantum model. multi-electron atom is a quantum model. That is also, that field is also known as the many body quantum many body theory. So now if we apply these are actually we call spin degenerate states. Yeah, these are actually the spin degenerate states, and we can split them based on, okay, actually it's not the spin, it's actually magnetic degenerate states. Spin is again, it will come inside. So these are the magnetic degenerate states, and these are the angular momentum degenerate states. And when multi-electron system, this angular degenerate states will like split into multiple, and each will have magnetic degenerate states. And if we apply magnetic field, these will again split. That's why we call it as magnetic quantum number. So so we can split those into again by application of magnetic field. Due to magnetic field, we can even split these energy states. And now how can we know that it is splitted or not? By studying number of monochromatic wavelengths in that radiation. Let's say from one radiation, we at this, it can only possible let's say if it is excited state this, and it can only relax this, and wherever it is, it will emit only monochromatic radiation. But let's say if it is, if it can excite, let's say now after splitting, it can relax here. Now it will emit one here, and it can even excited here also in that same energy level, and it can from here to here, their wavelength radiation will be different. From here to here it will be different. From here to here it will be different. So by identifying number of wavelength in that spectrum, that is called spectrum, which we can identify how many number of monochromatic wavelengths are present, we can identify the number of transitions involved. So we can identify these, that previously it was degenerated in these many numbers, but we can trace back these, it is these many states. But now after application of a magnetic field as a perturbation, then we found these many transitions involved. So we will trace back that each transition for each energy level. So that's how we can find these energy levels. And actually if we even more apply some more potential perturbations by increasing magnetic field or what, each electron can occupy two states, right? Two electrons will occupy here two energy states. And yeah, so this is how yeah, so these are the finally splitted energy states, and each state will occupy by two electrons. And these two electrons, if we apply some different kind of perturbation, these each energy state will be occupied by two electrons, right? So again this single one will split into two, and in the two only one electron will can only accommodate it, and that's what we call spin degeneracy. So actually in this energy level also two electrons are occupying same energy value, and that we splitted by a spin, that is we call this as a spin degeneracy. And that spin is also now splitted into two values. That will come by if we apply perturbation of magnetic field only, but it is in little advanced. But now you can understand this terms. Till here you might have heard the normal electronic configuration, which we also study. So this is what the degeneracy means, and spin degeneracy means these are the magnetic degenerate levels, and after this these are the spin degenerate energy levels, and these are the principally degenerated energy levels, which we identify as a principal quantum number. Okay, I hope this made you some understanding. I will explain it again. I will continue this in the next session. Thank you.